Okay, so we have been discussing about hidden Markov models. Let's quickly summarize what we read. I think this will help you to see the bigger picture. So the model is something like this. The model is right where this is z0, z1. Did we start from 0 or 1? 1 only, na? 1. 1, z2, some zn, and this z capital N. This is x1, x2, xn, and x capital N. This is my hidden Markov model. And so this model is trained using ML estimate, and more specifically EM algorithm. So what is the model about? So this model is you define some q, which is a function of theta and theta old as well, and you want to maximize this q with respect to theta. That will give you the theta, right? This is your theta star is the argmax of this. You want to optimize it finally. No, I'm sorry. Basically, there is a background that how this q derives, etc. So, without going into it, so you want to maximize some function, and you do it with the help of EM algorithm. EM algorithm has two steps. In the E step, you compute the likelihoods q z given x comma theta old. This is the capital Z, which means the entire series of so this is what is my E step, where I just estimate the, you can say, membership functions or the probabilities of the model, the membership function basically. We're not updating any thetas here. We're just estimating that how much of the data belongs to this cluster, something of that sort, comparing it with the k-means clustering, right? So E step is just to say, okay, this is my data and this is the membership of Z associated with that data, right? The second step is the M step, which actually optimizes your theta. So theta is argmax over theta q. And after estimating it, you will say my theta old is equal to theta. Theta old is equal to theta. And then you repeat this loop, right? You repeat this loop over and over again until convergence. So we have done the M step, and we have seen that the M step is very easy, right? Once you know the gamma, what is it called? Once you know your membership functions, for example, my mean is simply that weight membership function, weighted membership basically, weight times some x divided by summation over gamma, something like that, right? Something of this sort, right? Estimating gamma was done in the E step, and M step simply used these gamma values to update our parameters. So M step was very easy. But E step was a bit involved. It was also easy, but then you had to use the forward backward algorithm or the alpha beta algorithm to compute E. I mean, it was computationally expensive. To make it computationally tractable, we used that forward-backward algorithm, right? That start from the left end and move to the right end, that is alpha. Start from the right end and move towards the left, that is the beta parameter. And you computed gamma using those alpha beta things. So it's basically an algorithm to speed up your calculation of gammas, right? Somebody may say, can we have a simpler approximation, means a simpler way to estimate gammas? So what can you think of some simpler way to estimate gammas, which may not be mathematically very rigorous, but it may work? Means membership functions, no? Memberships. Do you know any simpler way? So in this case, the simpler way is that you have your model, you know your theta old or the parameters. Now you just instead of finding alpha beta soft membership function, find hard membership functions, right? That this data belongs to this z, or this data x comes from this value of z only. In other words, instead of saying my x, the probability of x given z, okay, I will write it down. Instead of saying that probability of x is equal to probability of x given z into p of z, sum overall z, instead of saying that, I can simply say p of x is equal to p of x given a particular z star, where z star is the z star equal to argmax, right? I do a kind of hard assignment. Instead of soft assignment, I'm doing a hard assignment here. This is computationally very easy. Doing hard assignment is very easy. And then I'm saving my computational cost of summing up all those entries, right? So something similar we can do with HMM also. In HMM, what happens? You make a trellis. There are different representations of HMM, right? We have discussed. One representation is this representation, this one. The other representation is state representation. I forgot the exact names, but it is like this. You have state 1, state 2, state 3, and then there are transitions, right? And maybe self transitions also, right? Let's say I spoke a word, apple. From A I go to P with this probability. From P I went to this with this probability, etc., etc. Right? So that could be one representation. And this diagram also. And then the other representation is a trellis representation, where we just say all my 4 seasons, summer, winter, etc. And then on the x-axis you have n, or time, and here you have k. Basically z is equal to k something. And k varies from 1 to 4. And then you have your transition things. So so when we compute this p of x, you take all possible paths, and every path will give you some pz, or in other words, some value of gamma. And then you will use all those values to update your theta, right here. To find q, you will use all those possible paths. But the approximation could be, instead of using all those possible paths, I will just use one best path. And I will just use that as a hard assignment and update my m with all those hard assignment values, right? That is the other, which means, in other words, you have in this you have updated your model, right? On this step, what you do a bit of decoding, find the top best path, and do a hard assignment that this is the only path possible, and then from that path again compute your m. Means again update your theta. Is it clear, or is it very difficult to understand. So what I'm saying is, in the beginning I have theta old here, right? I use my theta old to do a decoding, a hard decoding. I get one best path, then use that path to update my theta again. Then again use the model to do again a decoding with the new parameters. I got another path, use it to again then update your parameters, right? So this algorithm is computationally very, very less expensive as compared to the full alpha beta or forward backward algorithm which we discussed yesterday in the last class. But it has been seen performance wise both are comparable, at least for large data sets. The performance is almost similar. So you can save a lot of computation in the E step by simply using a one best path, the hard decoding. All right. Okay, now we are going to start the next topic. So what we have done until now is okay, let me first write down what we have done until now. If somebody gives me speech or audio and somebody tells me the corresponding sequence of observations, right? Corresponding sequence of observations, let's say that I am saying some sentence. My name is Ravi. Something like that, right? You have the entire sentence and you have this output. This is my, you can say this is my Z. Or you can break this down into a sequence of tokens. You can say this is Ma. I don't know how to write I. I don't know. Maybe there is some IPA symbol. I don't remember it. My name is I don't know how to write A. Some A. I don't know. Name is Ravi something. My name is Ravi. So I will say, okay, these are my Z values, like Z is M here, Z is I here, Z is Na here, etc. And then this is my X observation. I want to train my model, and then during inference, only given the X, I can infer what are the Z values. Right? That is one way. That is how ASR is done. So this will. But what is the output of this ASR model? What is the output? What is the output? A sequence of states. It's not the complete sentence, right? So let's say my model, when I did testing, it will, given any audio, it will output this symbols. But sometimes because of uncertainty, it may give some other symbols also. For example, it could be here is a U instead, an U sound instead of a sound. My name, it becomes my NUM is Ravi. So what will you map it to? How will you read that? Are you getting the question? That this model is returning a sequence of states. How do I map that sequence of states to the final sentence which I want to see? Like a sequence of words, right? And maybe also sequence of the entire word plus the diacritic, or what is the punctuation marks, right? How do I map this sequence of states to that form? That is the question, right? So for that, and also there could be spelling mistakes. How do I correct the spelling mistakes, right? So for that we use something called finite state machines. So today we will be discussing about finite state machines. How many of you have done ESC 201? Everybody has done ESC 201. So in ESC 201, you towards the end you read digital electronics. In digital electronics, you make some state transition tables and excitation tables, right? Right? So those are finite state machines. So you have already studied finite state machines in that context. But today we will discuss it in the context of audio or speech. So, okay. Let me write down first, where do we need finite state machines in audio? You have spellings. Technically, it is called the dictionary or lexicon, which means it maps your words to phonemes, or vice versa, phonemes to words. But if you open a dictionary, you will search for a word, and for every word, phoneme sequences are given. Have you seen in your dictionary the phoneme sequences? You can check any dictionary. It will contain the phoneme sequences in the IPA form, mostly, if it is an English dictionary. Yeah. So this is where to do it with a model, you can use a finite state machine. Basically, it takes as input, it can take as input phonemes and it can return words, or it can take as input words and return phonemes, either way. But for ASR task, my input is sequence of states, or maybe you can say phonemes, and then I want to return words in the output. So that is the mapping which I want to use. For example, my input could be okay. Input could be na.
So is this a classical rule-based method, or is it also trained on data?
It is a model. It can be built using rules, and it is generally what do you say, kind of data structure, where you can very efficiently, people have developed very efficient algorithms to construct these finite state machines and to do different operations on finite state machines. I will discuss those operations.
I meant if it was trained on actual data of mappings from phonemes to words.
Okay. Yeah. So you can train this finite state machine on the data, depending on what do you call as the training parameters. Let's say if your connections between the states, they are the training parameters, then you can feed your dictionary and you can construct this finite state machine from there, right? But there are also weighted finite state machines. Weighted finite state machine means all the words also have some probabilities associated. For example, some words are more frequent than others, or some ways of speaking is more frequent than others, of that sort. So it's called a weighted finite state machine. So there you have weights also, and if you wish to learn those weights, that is also possible. Although those are not very standard things, means people use very simple learning algorithms there, simply ML estimate, or which is very simple ML estimate. So generally we don't study them very rigorously, but yeah, there are methods to do that. So in this course we will not be learning those weights, but if you wish to learn, you can. Means we will be discussing some learning, but very basic, just from data. It's like one-to-one mapping. It's not probabilistic learning. Okay. And then if there are spelling mistakes, let's say v, u, na, then you may either raise a flag saying that this is the wrong spelling, or you may convert this into, you may still map it to 1. Either way, means depending on how you want to construct it. What is the application? The other area where finite state machines are useful within ASR is in grammar or in the language model. let's say I give a sentence as input, I am eating. Is this a valid sentence or not? Valid English sentence or not? Yes. I say, I were eating. Valid sentence or not? So this is not a valid sentence. So this is, or you can say I is eating something. That is not a valid sentence. So basically, there are many grammatical rules, or you can say syntax, which sentence is supposed to obey. And if your sentence does not obey that syntax, then it is not a proper output of your ASR system, right? So this finite state machines can be used either to raise a flag that this is incorrect input, or it can be used to induce those corrections automatically. And third area where it is also useful, where it is actually most useful, is to eliminate certain possibilities. For example, if your model is confused, did you say I am eating or did you say I may eating? Right. So two possibilities, and then to decide which one is the right option, you can use finite state transducers. They will basically eliminate those improper outputs. They may be high confidence outputs, but you can eliminate them, and then the more confident output, the correctly formed outputs are then finally passed through. Right? That is the most important use of FSTs or FSMs, finite state machines. Right?
So sequence which we give the finite state machine, are the spaces already included, or is just the sequence in the finite state machine itself identifies where to break the word, start a new word?
Oh, the lexicon will do that. The lexicon can break it down into multiple words. No? For example, I said recognize beach. What did I say? Can you recognize beach? You will say, can you recognize speech? But I said, can you rec a nice beach? So it's just an example to say we can break the word into possibly multiple ways, but then your FSTs will come into picture, that they will assign some probabilities, and then depending on what I said and what was the FST parameters, you will output the most probable outcome. Right? Does that answer your question? Okay, we'll move on. So we won't be spending too much time on finite state machines, so I will move a little faster. But there are YouTube videos, the lectures which I delivered maybe 2 years ago. They are on YouTube and publicly available. There are 3 lectures, I think, so you can watch them to know the details, right? And I can share a paper with you which describes the finite state machines. So I will share it, so you can read that paper also. Okay, so we are starting. Okay, so now let's see. So what we are doing is we have sequences of discrete tokens. These tokens could be phonemes, or these tokens could be words, or these tokens could be anything, but they are discrete tokens. And our we want discrete tokens, sequences of discrete tokens. So finite state machines are machines or models whose input is a sequence of tokens, a sequence of discrete tokens, and output is also a sequence of discrete tokens, right? Nothing continuous here. Input is also discrete, sequence of discrete tokens. Output is also a sequence of discrete tokens. And those tokens may come from different alphabets. Alphabet means that the set of possible tokens. the set of all possible tokens that is called the alphabet. For example, when I write a sentence in English, there are 26 characters which I can use, right? So if I consider every character as a token, then my alphabet has a size of 26, right? I have 26 size alphabet, and from those alphabets I can construct so many words, like all the books are written using those 26 characters. Or you can include space, and you can maybe include some punctuation marks also. So then your set may become a little larger, but still it is a finite set. So which means it's a discrete, it's a sequence of discrete tokens. Okay, then so finite state machines are used for two purposes, either to check the allowed sequences, and the applications could be, how many of you have used Google Forms? It's just a wake-up question. So you have used Google Forms. Sometimes when in Google Forms you write your email ID, it gives an error saying that you did not input email ID properly, or only input an email ID or nothing else. Sometimes it asks you to input a phone number, and you enter something, then it will give an error message saying that you should enter only a phone number, right? So how does it do that? So you can use finite state machines to do that. It's a data structure which is very efficient to do that task. Of course, you can make some other kind of rules also, but finite state machines, they give you very efficient data structure to do that. So format check. Then you may do sequence to sequence mapping. For example, in ASR, you want to map the sequence of tokens or sequence of states to the sequence of words. Or you may want to map sequence of words to the final sentence, which is also sequence of words but with corrections, etc. Right? So all those tasks can be done with the help of finite state machines. So within this sequence to sequence mapping, you could also do spell check here, or even do spell correction here, which means my input spellings were wrong, but you can map them to the right spellings. Or you may do it for transliteration. That I wrote something in English or Roman script, and I want the output in Devanagari script. That's also possible. You can also use it for translation, but translation will be very inefficient here, because in translation the word order also changes. When I say, when you say, मैंने उसको किताब दी, तो पहले आया मैंने, फिर उसको, फिर किताब, फिर दी. But in English it will become, I gave the book to him or her, right? तो I मतलब कि पहले तो आया, but then मैंने उसको, so he or she or that came first. So the order has changed, right? So मैंने उसे किताब दी. I gave him. तो बुक यहाँ चला गया, दी यहाँ आ गया, उसे यहाँ आ गया, मैंने यहाँ आ गया. So the ordering also has changed, no? So that's why FSTs become little inefficient they are very inefficient for translation tasks. But yeah, in principle they can do it, although very inefficiently. Okay, now let's discuss. Now these were the examples to motivate why do we need finite state machines. But now let's see the mathematics or the theory behind. First thing we are going to study is finite state automaton. Finite state In English, it is in singular form it is automaton. In plural, it will become automata. Finite state automata. So, finite state automata will look like this. Let's say I want to tell whether this sentence is proper English sentence or not. All right, whether this sentence is a proper English sentence or not. So I will construct an automaton. You can see it is like a set of sequences which are correctly formed or which are allowed, right? So my finite state automaton is a set of, so this it's like is a set of allowed sequences. It is a set of allowed sequences, but then those sequences are represented in a very, very efficient way, very, very compressed form. So how do I represent it? Let's say I want to represent the sentence I am eating. Every word is a token here. Okay? So every word is written on the arrow, and then my states are there. So every input is written on the arrows, and my state is state. So this is state number 0, state number 1, state number 2, state number 3. Do you remember your ESC 201 course now? You had some states 0, 1, 2, 3, and whenever, let's say I'm sitting on the 0th state, I see the word I move to the first state. Then I'm reading the sentence from left to right. I see the next word is am, then I move to state number 2. Next word is eating, I move to state number 3. And now my sentence is over and I want to accept it. So I should mark this as the final state. So I draw a double ring to show that this is the final state, which means if I have reached this state and my kind of input has terminated, then I can say I'm done. Means this is accepted. The output is an accept. Yes, I accept it. And likewise, which state to start from? I have to mark that. So this is my initial state, so I just make it bold. So this is my, okay. This is my initial state. This is just any state. And this is my final state. All right. So these are the inputs. Input token. And this is the sequence of input tokens. Right. Now if I give it the sentence, I will be eating, will it accept it? Will it accept it? I will be eating. It won't accept. Why? Because first word it will read I. First, in the beginning it is sitting at the 0th state. It reads the word I, it moves to the first state. Then it sees the word will. It will not move anywhere else. It will just keep sitting at 1 only. So hence it will say rejected. Your input is rejected. Right? Your input is rejected. If I give it the input I am, will it accept or reject it? Accept or reject? It will see I, it will move to state number 1. It will see am, it moves to state number 2. Then there is no further input. So it stops. But it is stopping at a state which is not the final state. So it will reject it. It will not accept. Okay. So for accepting, it has to reach the final state. Okay. This is one kind of finite state machine. Other kind of finite state machine is a finite state transducer. See, finite state automaton has no output. It has no output. Its output is only accept or reject. It's a binary label, accept or reject. It's not another sequence of tokens. But now we are going to see finite state transducers. So finite state So finite state transducers also have an output. So it has got input and output. So for example, let's take the example of spelling correction. How many of you have the surname Agrawal? How many of you have the surname Agrawal? Nobody. Nobody is Agrawal. Okay, how do you spell your spellings? Agrawal, Agrawal, Agrawal. So many possible ways you can spell Agrawal, and I personally see, like, whenever I have some Agrawal friend, they spell their name differently. So can you make a transducer, a finite state transducer, which will take as input a sequence and it will map it to the right spelling of Agrawal? Means, okay, there is no right spelling, but some standard spelling of Agrawal. Maybe let's take the first one, whatever it is, as the Agrawal. Can you make a finite state transducer which will take as input all these 4 variations and it will normalize it into a standard form? Can you do that? So this is what finite state transducers do. And how do they do it? They have start state. Now here, what are my tokens? Letters are the tokens. Let's say I saw an A. Then I saw a G. The output can be an A. When I see a G, output can be a G. Then I have 2 different possible paths. I may go to a double G. In that case, it will map to G. Then I can go to an A. Output will be an A. This is the first sentence, the first this thing. It maps to the right thing. But I could also have a second option. So in that case also I have to map. So what is simplest method is, I can just draw the same thing again. Right, A maps to A, G maps to G. Then I have no second G, so I have to introduce an empty maps to G, and then we have R followed by A. So R maps to nothing, then we get an A, then it will map to A, then input is an empty R, then W maps to W, A maps to A, L maps to L. Right, so in this way I have to create all the possible paths, right, 4 paths, A, G, R, A, W, A, L. And in this way, so I have to induce some empty tokens, blanks, to basically match their lengths also, right? So in this way I will create 4 more. That's a valid finite state transducer. Got it? But this example, let's say you got an A to start with, right? You got an A to start with. In the input is, let's say, this one. I got an A. I'm sitting at state number 0. Now, which state I should move to? This state or this state? Or other 2? There are total 4 states. I can reach there by following an A. Which state should I move to? To this state or this state or this state or this state? There is a confusion here. So this kind of an FST is called a non-deterministic FSC.
Sir, in this,
Hmm.
from the second branch, can't we just pull out all the other branches?
Yes, yes, good. So, as you suggested, the other possibility is I just merge all these branches into a single branch, and if I see an A, I go here. If I see a G, I move here. Now here, if I see a G, I move here. If I see a blank, I move here, and there I do that. So I can convert this FST into another form of FST where there is only one path or one transition possible for a particular input, right? One input maps to only one transition. Here, one input, same input like A, it maps to 4 different states, right? So let me write it down. So in non-deterministic FST, you can go down multiple paths. Because same input maps you to different states. But in deterministic FST, you don't have this problem. So if you're sitting in this state, you see some input, there is only one path where you can go to. So it's called a deterministic FST. So you have single path possible. Means you see some input, you know very deterministically that this is where I should go. So in non-deterministic FST, generally what people do is they will now make 4 paths, and then ultimately they may eliminate some of the paths, right? For example, they saw A, G, they are moving in 4 parallel paths, and then they saw a G again. So all these 3 paths are eliminated, only this path is, it will stay, it will be retained. But that's very inefficient computationally because you have to simultaneously traverse multiple paths. So that's why deterministic FSTs are computationally more efficient. Okay, so that being said, now let's see how do we do it in program. In a program, generally to specify an FST, you just need to specify a column of initial input state. No, the tail, the head, the input, and the output. That's it. Just fill up this table and you are done, right? Let's start with this example, I am eating. In the I am eating example, the input is you are on the 0th state first, and when you see the input I, the head state becomes 1, and then if you're sitting on 1, you see an am, it goes to 2, and when you see eating, then you go from 2 to 3. And then if you are at 3 state, you have no final, nothing final basically. That's it. So in FSA, finite state automaton, there is no output column. And in FST only you have output column, right? So in this way you can specify your FSM. There are programs, libraries available which can construct FSMs. If you give this kind of a table, they will construct the kind of data structure for you. And one such library is called OpenFST. So if you can go to the website openfst.org, and there you can download this library, and then you can start just programming. Just give this as an input file and you have created an FST. Okay, now what are the operations possible on different operations possible on finite state machines. One operation is called union operation. What does union do? So if I have a finite state machine A and another finite state machine B, then let's say if X is a sequence, let's say if my capital A is my alphabet, then if X is of length n, then a to the power n. Is it confusing? A is capital A. This calligraphic A is my alphabet. Like let's say the words of English, the letters of English, A B C D E F G H, is a set, and a to the power n means you have a sequence of length n coming from this alphabet. If every token coming from this alphabet. Yeah, so let's say this is the case, and the X is accepted by A union B if and only if X is accepted by A or X is accepted by B. Right? Let's say you have a sentence, I am eating. This is one FST, one FSA. You have another FSA, I will be eating. And now you take a union of them, and if my input string is I am eating, this AUB, the union thing, will it accept this sequence? The answer is yes, because it is accepted by one of A or B. I know A accepts it, so A union B will also accept it. So union means if X is accepted by A union B, then this implies that it is accepted by either A or B. The other possibility is concatenation. Concatenation, what happens is, if X is accepted by A, Y is accepted by B, then you concatenate the two sequences. XY is accepted by AB. AB is the finite state machine which is formed by concatenating two finite state machines. Let me give an example. Let's say if I say one finite state accepts only I am. Or it could also I was. This is finite state machine A. Another one is eating or going. This is the finite state machine B. What is the meaning of A concatenated with B or AB? It simply means, make a connection here. And this connection is a blank, input is blank, right? And then convert these nodes into the ordinary nodes, simple ordinary node. Instead of initial or final nodes or states, they become ordinary states. That's it. So this is an example of AB. This is concatenation. Like that, you can have many operations. I will discuss some important ones. One is called closure. In closure operation, what we do is we have A it means I can repeat A multiple times, B will stay, C can be repeated multiple times, D, E. So for example, sometimes you may want to allow repetitions, right? Let's say in English you can say I am eating, 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 and only eating. Right? So it's a valid sentence. So what you can say, what you will have to say here, I am eating and only eating. So I may say here a plus sign, which means this should come at least once. I can say I am eating, but then I can repeat it multiple times. Eating, 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 and only eating. It's a valid sentence. And this is how I, instead of writing eating 100 times or whatever, or instead of writing all those sentences or all those possibilities, I simply write a plus sign on top saying that you can eat as much as you wish without writing so much. So now somebody can say, so this, what is the meaning of this star? Star means some things can be omitted also. Some things can be omitted also. What could be an example? I like to drink maybe something. I like to list of things, yeah. So that's what I'm trying to do. I like to I like to shower and eat and eat and eat and eat before sleeping. So you can say here, right? I can say I like to shower before sleeping, perfectly fine. I like to shower and eat before sleeping, perfectly fine. I like to shower and eat and eat and eat, so that is also perfectly fine. But instead of writing, I can simply say a star, right? So these are some examples. Somehow we ended up with these examples because maybe the sequence of events took us in that direction. But it could be something like a phone number. A phone number. No, but phone numbers are also finite. Okay, think of something. Okay, so these are the closure operations, and how do we represent them in the machine? In the machine, we have, let's say, I am eating, but then this eating thing and only eating. This is the final state, this is the initial state. Now, what do we do in between to make it repeat multiple times? One possibility is, one possibility is you can do it like this, with a blank, right? This means if I come here, I see an eating again, then I can again traverse this path, and if I don't see it, I can move straight, right? So this is an example of plus closure, like a plus symbol. Other possibility is that I can make a loop like this, saying eating. This is a deterministic FSA. Oh, what you can say. Yeah. Here you know exactly, if you see eating, you move here. If you see and, you move there. This is another possibility. Okay, now what about the star thing? Oops. I like to shower, etc., etc., etc. So just I will say, okay, just Oh, how will you represent this one? And eat. So one possibility is this. Right? Since and eat both are on that self loop, so that I can say I like to shower before sleeping, I like to shower and eat before sleeping, I like to shower and eat and eat and eat before sleeping, something like that, right? So this is a valid FSA. Yeah, that's it. These are two important. And then another important operation is intersection. Intersection means X is accepted by A intersection B if and only if X is accepted by A and X is accepted by B. Right? So if my X is accepted by A as well as B, then only it is accepted by A intersection B. Right? So let's say my A is I am sleeping, I am eating, I am drinking, I am going, all those possibilities, and B is I am sleeping, I am eating, and I am dancing. What is the A intersection B? Only those two things which were common. I am sleeping and I am eating. Right? Other things will not be accepted by A intersection B. Right? Other operations are
FSM and FSA.
it could be anything, FST or FSA. These are operations are possible on FSMs, which includes both FST and FSA. Determination and minimization. What is determination? You already know, right? That there should be only one path corresponding to an input. Means if the input is this, then I should have only one path to go. I can't have multiple paths for the same input. And what is the meaning of minimization? Minimization means, can I change the structure in such a way that it runs very fast for runtime, for minimum runtime. So these are the operations, determination and minimization. And then there is one very important operation which is called composition. So what does composition mean? Composition means that if X, this is generally true for FSTs only. This is only for FSTs. If my X, sequence X maps to sequence Y by A, means the transducer A maps X to Y, and another transducer B maps from Y to Z, then X will map to Z by A composed with B. It's simply like composition of functions, right? So A and B are like functions. They take some sequence of input as sequence of tokens as input, and sequence of tokens is the output. And A and B are like functions. So did I write it? Okay, the ordering is different. In functions, we will write it as B of A, right? But in this terminology, we write it as A O B. So in mathematics, we write B of A of G, or B of A of X. But here in this terminology, we write A of B, which means you have your input X. It first goes through A and then goes through B. Therefore, you call this as AOB. Right. All right? X. That's it. So how we do it in practical scenario? We just construct very simple FSTs using simple rules. For example, I am eating, I am sleeping. Just put them together, and then allow the library to do the magic. You want to have it a deterministic form. Like we start from this Agrawal example, and you just construct these simple things with your program, and then you can simply apply the operation, make it deterministic, and automatically the library will do the magic. It will make it deterministic. Then you will say, oh, I want to have it minimized. It will do the minimization. Then you say, okay, I have 2 FSTs, I want to concatenate them. Just with one command you can concatenate 2 FSTs, right? So the library does the magic. If you want to read the algorithms, then you're welcome to read the book, the paper which I'll be sharing, or you can go through the lectures on YouTube which I gave some time ago. Now, how do we do it in ASR? In ASR, one FST is formed by the lexicon that map these set of states or this sequence of states to this sequence of words. Another FST is formed by the grammar or the syntax, that these are the allowed sequence of words, these are not allowed. Now what operation will you do to make the final model? What operation will you do? You have 2 FSTs, and to get the final sentences in the output, what operation will you use? Composition, right? Compose them. So the input here is the sequence of states, output are the words. Here the input is the words, output are the sentences. Just do a composition. Compose them and you get an ASR system. All right. Then there is a concept of weighted finite state transducers. This I'll briefly mention. I've already kind of told you in the beginning. So it has another parameter called weight parameter. Let's say if I say I, or let's say if A maps to A or something, A maps to G, then there is a weight also associated. It says 0.1 weight. So in this way you can have a weighted finite state transducer. It has weights. So finally what you will get is multiple outputs possibly, right? At this sequence of states, this input maps to these multiple outputs, for example. Then you can use the weight to find out which is the best output, right?
How is this different from an HMM?
How it is different? In HMM, you have hidden states and you have few observations and then lots of probabilistic parameters.
Here also we are getting an output on transition and we have assigned. So are these weights similar to probabilities, like transition probabilities?
Yes. Yes. So this is like transition probabilities.
Yes.
Yes.
So it is an HMM instead. It's like,
Yeah. Yeah, just that in HMM, your input x is a continuous random variable or a vector, but here it's a discrete random variable. And the mapping is also kind of unique. If you get an input A, it will map to output G with this much probability. Yeah, there is no scope of multiple paths here. The multiple paths come from HMMs, right? Multiple paths come from HMM, but here single path will map to single path only. It will just carry the weights. Let's say my HMM gave me that this is the path with this much probability. Now I pass that path through this weighted FST. What will I get? I will get again that path maps to another sequence, sequence of something, sequence of words, for example. Plus these weights also will get added or multiplied with that original weight, original probability. So those probabilities change, but single input sequence maps to single input sequence, right? Okay, to summarize once again, HMMs give me multiple possible paths plus the probability of every path, right? I pass that everything into the WFST. It will map each path to each path. Maybe some paths will be eliminated also on the way, but all those multiple paths may end up in multiple paths, and those probability values will change because of the weights. Right? So finally I will get another multiple number of paths with different weights, and then I can choose whatever is the best weight. Right? The advantage of FST is that I am also inducing more information into my model. The information about lexicon, information about grammar, and since everything is very modular, very decoupled, I can change it as per my desire. For example, the word COVID was never there a few years ago, before 2019, for example. No, this word did not exist, but suddenly this word has appeared: COVID, quarantine, and all those terms. So what do? Should I retrain all my ASR models, or should I just change the FST? I just include another path saying COVID is a valid string, right? This is much simpler, no? So it makes everything very modular. So you just add one extra path, and your language, your ASR will now output new words also. COVID is also an output. Yeah. So that's the advantage of using FSTs. But yeah, that's a good observation that these are transition probabilities. Well, many times these FSTs are considered as reweighting our lattice. You have we saw our lattice previously, right? Our trellis or lattice. So this FST will reweight. Why? Because these weighted things, so all those initial paths, they will get reweighted. So you will read so many papers, if you read papers in ASR, reweighting techniques or reweighting methods. So basically, which is talking about FSTs. Okay. Thank you very much. That's it. Now we are moving on to the next topic, which is music. So we'll be doing, our goal is to do a project. You will receive some audio recording. There are 3 possible projects which you can take up. I have thought about 3. If you have anything else in mind, you can tell me that also. I will share with you some classical music recordings, let's say some songs by Pandit Jasaraj or by M.S. Subbulakshmi, or all these famous personalities probably. And then one project is to determine what is the tonic frequency or the bass frequency they are singing at. You will learn these terms, don't worry. The other thing is estimate the tal, what strokes are being played there, what is the BPM, etc. Another problem is estimate the melody of the main singer, right? Like what are they singing, sa re ga ma pa dha ni sa, etc. So what frequency they are singing. So these are 3 possible projects which I have identified with the help of Parampreet. And now Parampreet will just tell you a little bit about music, and then in the next class, Parampreet and I will try to discuss the basic theory you need to solve these projects. If you have any other project ideas, we are welcome to share. They will be polyphonic, like their original performances. Okay. I have to go. I have a. Acha.